Today we are going to learn about integration by parts, which is another method of integration that you can use when you are trying to do something that you can't integrate normally or with U substitution. I'm going to just push my way through this and go through it kind of quickly to get it hopefully all done in this 15-minute time frame. So remember that you can always pause and restart the video as many times as you need to help you learn the material. So here's a brief explanation of why you need integration by parts. The main thing I want you to understand from this is that it's a theorem that helps you relate the integral of a product of functions. If it weren't for this method, you wouldn't be able to take a problem that the derivative was found with the product rule and go back and integrate it. So it's really for something where somebody took the derivative of two things multiplied together and now you need to go backwards. So I'm actually going to derive the formula for you quickly so you can see where it came from. Well, the first thing you need to do is you need to start with the product rule for derivatives. So the product rule for derivatives just looks like this. You're taking the derivative of two things multiplied together with respect to x. So the derivative of u times v would be u times dv dx plus v times du dx, or first times the derivative of the second plus the second times the derivative of the first. And so here you can see now I've just taken and done a little bit of changing to the problem here. So the first step, what I did is I just dropped the x's, so you could look at it in our normal way, u dv plus v du. And then I solved for u times dv, because this is actually what we're interested in, this thing here. So we're rearranging it so that u dv is by itself. And then in my last step, I really just got u dv on the left-hand side. So now what we want to figure out is how to integrate this thing. So that's what we're going to see on the next slide. So we want a way to differentiate this kind of weird UDV thing, and it's actually right here in this problem. I just have to simplify it. And this is called integration by parts. So basically all I did was, so you have two things multiplied together, u times dv, and notice that this integral right here is the derivative, the integral of this derivative. So the integral and the derivative cancel each other out. They're inverses of each other, and you're left with this integral of v du. Okay, when I was in college, I learned this as ultraviolet voodoo, u times v minus v du. Whatever you can do to help you remember the formula that works for you, great. Okay. Right. Sounds totally strange, and you go, what in the world am I supposed to do with this information? So what this means is that if you have an integral that has two parts to it that are multiplied together, so that u and that dv, and you can't solve it by integration by substitution like we did yesterday, then you might be able to use integration by parts. There are typical types of integration by parts problems, and they will have two of the following types of pieces multiplied together. There are 5 pieces, and there are usually 2 of these pieces multiplied together, usually. So here are the 5 possible pieces. So they could be logarithmic, could be inverse trig, could be polynomials, could be exponential expressions, or trigonometric expressions. So those of those 5 choices, you will usually see 2 of them multiplied together. And if you see that happening, then that's a candidate for integration by parts. Okay, so there are 3 processes for integration by parts. We'll start off with the basic process, then I'm going to do a process called tabular integration, and then we will do one that I call solving for the unknown integral. All 3 are still integration by parts. They're just solving it in a slightly different manner to make it easier. Okay, so for the basic process, 3 steps. The first step is to make your choices for your U substitution and your DV substitution. You'll be doing 2 substitutions, and you'll make your choices for each of them, and I'll explain how on the next slide. The second step is to find your du, so you'll differentiate u to find du, and integrate dv to find v. So you're going to be doing both differentiation and integration in the same problem. Third step is then to just fill in that formula, that ultraviolet voodoo formula, and then solve. So let's see our first example. So the first example is x times sine of x dx. So this problem is a candidate because you have a polynomial and a trig function multiplied together. And you need to decide which thing is going to be your u, and which thing is going to be your dv. And the way that I tend to remember it is I have this mnemonic device that's called LIPIT. And LIPIT stands for logarithmic expression, inverse trig expression, polynomial expression, exponential expression, or trigonometric expression. So each of these letters stand for one of those 5 types of expressions that we learned a couple slides ago. In this order is how you choose your u substitution. So whichever of these appears first in your problem is what you choose. Meaning if you have an inverse trig and an exponential in the same problem, inverse trig will be your u sub. So in this problem over here, I have a polynomial and a trig expression. So the polynomial expression, p comes before t, so p is my u substitution. So my u is x, and therefore what's left over is my dv. So I have now, for my next step, I have to integrate the dv and differentiate the u. Okay, so let's go ahead and actually solve this problem. So get my pen here. So the problem we're integrating is x sine of x dx. And using the formula, we are going to first take the derivative of u, which is just dx in this case, and the antiderivative of sine, so integrate this piece here, which happens to be negative cosine of x. Excuse me. Okay, according to the formula, we do u times v first, so u times v will be negative x cosine of x. And then I'm going to do v times du. I'm going to do negative cosine x dx. So I'm going to turn this into a positive cosine x dx. And now I have to integrate the part that's left over. And in this case, it's not really a big deal. I just need to integrate cosine. And we know that the antiderivative of cosine is just sine. And then, of course, we can't forget our plus c. So this is our final answer to this u substitution problem. Sorry, this integration by parts problem using both a polynomial and trig. Show you how to do what's called the tabular method, which tabular method is used when you have a polynomial expression and that polynomial expression has a power greater than 1. So if it's just a power of 1, you do it like the way we just did it. If the power is greater than 1, then you want to use this tabular method. So I'm going to again show you the steps and then walk you through an example. So you'll still pick your u substitution and your dv substitution, but you're going to make a table out of those pieces, with the left column being your u and the right column being the dv. And write them in at the table at the top. Then what you'll do is, for each of the columns, you'll differentiate the left column, which is the u column, and integrate the dv column, which is the right column. And you do this until the differentiation column goes all the way to 0. Then, after you've done all of that, you will diagonally multiply the u's and dv's together, alternating their positive and negative powers for your final answer. Now, this won't make a lot of sense until you see the example, but write the steps down so at least you have them, and then you can use them to go back and look at the example. Okay, so here's our first example. So this one is x squared cosine of x dx. Still follow the LIPIT rule, so that means your u substitution should be the polynomial, which is x squared. So here's my left column, here's my right column. In the u substitution column, I'm going to put x squared in the first spot, which means in my dv substitution column, I'm going to put cosine of x dx. So that goes there. And now what I like to do is I'm going to differentiate this column until I can't do it anymore because I get 0. So I know that the derivative of x squared is 2x. The derivative of 2x is 2, and the derivative of 2 is 0. So now I stop. I'm going to end up with 4 rows because my last value here is 0. Then I take the antiderivatives of this column all the way down to equal or get across from 0. So the integral of cosine of x is sine of x. The integral of sine of x is negative cosine of x. And the integral of negative cosine of x is negative sine of x. And I'm noticing now that I should not have written Those dx's on here, we don't need those, so just ignore those. Okay, and for our final answer, we draw these diagonal lines down to connect the first thing in the left column with the second thing in the right column. So it'll be x squared goes to sine of x, 2x goes to this spot, 2 goes to 0, to this last one, and the 0 connects with nothing. And then you alternate between positive and negatives because you would be subtracting somewhere if you were to do this all the way out. So positive, negative, positive. If I had more rows, I'd have another negative, then another positive, and so on. So our final answer is this guy right here. Let me move it out of the way so you can see it. So the final answer, if you were to combine everything, will be x squared sine of x plus 2x cosine of x minus 2 sine of x plus c, of course. Okay, and again, it's coming from doing all that diagonal multiplication. Okay, so let me get this out of the way. Let's go on to the next problem, the next process, and then the next problem. So the next process is called solving for the unknown integral. And this is used when what your u substitution is doesn't ever differentiate to 0, and your dv never goes away either. So you end up having to repeat basically the basic process more than once. Okay, so this type of problem will happen generally when you have something that's exponential and something that's trig. This is the most common. So I'm going to go through this, and again, remember to pause and restart if you need to as we go along. Okay, so using our Lippitt rule again, we have an exponential and a trig. So the exponential e to the x becomes our u substitution, and the cosine x dx becomes our dv. And just like before, we need to differentiate the u, so that gives me e to the x dx, and integrate the v, and the antiderivative of cosine of x is just sine of x. So our normal process, just like before, is you multiply u times v. So e to the x sine of x goes here in this spot, and then it's minus v du. So minus sine of x times e to the x dx. So notice that really we've created basically the exact same problem again. We've just traded out the cosine for the sine. So we're going to repeat the process, and you can probably guess what's happening, but we still need to repeat it anyways. So now I'm looking at just this integral, and I'm filling in my u and my dv from the second integral that we have there. So my u, again with Lippitt, will still be e to the x, and my du will still be e to the x dx. And now my dv changes. My dv is sine of x, and my v is the antiderivative of sine of x, which is a negative cosine of x. So again, we're going to fill in the formula. Well, this stuff stays, so I can't get rid of the first part. So it's e to the x sine of x minus, I need to take the integral of this second piece here. So let me create a parenthesis here. So this is going to now be the u times v. So e to the x, negative cosine x, minus the integral of v, negative cosine x, du. Well, that's e to the x dx again. So if you'll notice, I'm actually right back where I started with the original problem. So now what I'm going to do is I'm going to add the negative integral on the right-hand side over here to the other side, to the left side. So now I have 2 of the integral e to the x cosine x dx on the left-hand side, and all of this is what's left on the right-hand side. So I'm going to put this down here. And all I have to do now to actually solve for the final answer is to divide this, we'll divide both sides technically, by 2, and that will give me that the integral e to the x cosine x is equal to e to the x sine of x plus e to the x cosine x, all divided by 2, and it's getting really ugly around here. Plus, don't forget our lovely